All right, in this one we're going to talk about universal gravity. And so it's also one of our forces that we were looking at before. Now, most of you are familiar with little g, and that is the acceleration due to gravity. Okay, and we know it on the surface of the Earth as 9.8 meters per second squared, okay? That's not what we're talking about. We're talking about the force of gravity. Now, as we'll see, the force of gravity is created by the universal gravity law, and it's where we get this 9.8 meters per second squared, but it's not what actually happens. So normally, if we're talking about the force of gravity on the Earth, we're just talking about a mass of whatever is on the Earth times little g, right? But that's a simplified one that's only good for the Earth. Truthfully, there is a universal gravity that states that all things with mass have an attraction towards one another. So that means if you have mass, and the person you're interested in has mass, then technically you two are attracted to one another. So you might think that and see your beloved other from afar and say, I feel we have an attraction. The great problem with this is the Earth has way more gravity and more mass, therefore more gravity, so you're going to be more attracted to the Earth. And that's why both of you might fall on your face instead of reaching one another. Now, this universal gravity, that's enough with my bad jokes. All right. This universal gravity, though, is represented with a simple formula of F of g is equal to the gravitational constant, capital G, times the mass of one object, multiplied by the mass of a second object, divided by the distance between them squared. And that's the distance between their center of masses. That becomes really important, especially for really big objects like the Earth, because that means we're looking at the radius of the Earth in order to get this gravitational constant. Now, I can already hear you complaining. What does this crazy formula have to do with that 9.8? Why can't I just use my, F of g equals m times little g? Isn't that gravity? Well, no, because it's universal gravity and there's a greater scheme. Let's take a look at it. All right, if I'm breaking this down, I'm saying that we have that formula of universal gravity is F of g equal to big G times mass of, this time I'm going to make it specific for the Earth. So I'm going to say the mass of the Earth times the mass of someone like me, divided by, and this time instead of the distance, I'm going to go ahead and say this is the radius of the Earth squared. Okay? Now we can see a little bit more where we get 9.8 from, because this constant is going to not change. It stays the same. It stays this lovely number up here. The mass of the Earth, it doesn't really change a lot. It's really huge, but it stays about the same. Yes, every now and then a meteorite might hit it and it might gain a little mass, but for the most part, the mass stays exactly the same. And then the radius, it doesn't really change the radius much at all. So if you're talking about the surface of the Earth, that distance is going to be about the same. So we can put all of this together and look at just this amount, because truthfully, there's another thing to this. If I say that F of g equals this gravitational constant times the mass of the Earth times the mass of me divided by the radius between them squared, but it also equals m of little g, well, I get this by dividing both sides by that m, right? That would cancel out there, cancel out there, and so we would have a new statement saying that, that's the wrong one, saying that g times the mass of the Earth divided by the radius between of the Earth squared is equal to little g. And I put all the numbers up here so you can actually type it into your calculator. And if you type that into your calculator, make sure you get all of the scientific notation down, you're going to get that it does indeed equal 9.8, it's like 1, and then some other numbers. Meters per second squared is what you would end up if you're canceling out the units for these. All right? So that's where all of that comes from. And then you just multiply it by that mass of whatever you're trying to figure out is on the Earth. That would be the second object. And we're still assuming it's on the surface of the Earth, and that's where we get this number from. So it came from the universal constant. Now, we've already seen that all of these are true. So this is our universal force, or universal gravity that creates the force of gravity between two objects that have mass. We can apply that to the Earth, and we get the mass of the Earth and the radius of the Earth, and we get to where we have the force of gravity on Earth, and we can understand that that section of this is equal to the acceleration due to gravity, and so we know to get this. So with this truth, we can take a look at something very important with this, that gravity isn't the same even on Earth everywhere. Let's do a thought experiment. So let's think about if you had a hole through the center of the Earth. So let's say we were able to dig a hole directly through the center of the Earth. We'll make it a big hole and a magical one at that. It's magical because it doesn't allow you to, be crushed or burn up or any of that stuff, and it manages to go through a liquid outer core as well as a solid inner core, things like that. So we have this magical hole now going straight through the center of the Earth. And we decide that we want to jump down. So the center of the Earth, right about here, here's us jumping down the hole, right? Well, our acceleration due to gravity on the surface is 9.8 meters per second squared. But what do you think it would be halfway to the radius of the Earth? Now, yes, I could go back and I could look at my radius of the Earth and I could cut that in half and I could do my entire calculation again. Or I can just go ahead and say, well, wait a minute. If little g is equal to this, that's not an F, that's an R. Then, and that's equal to 9.8 meters per second squared, then can I just find out what that acceleration would be if I was only 1/2 of that R, right? And then I can go ahead and do this, and I can say, wait a minute, well, that's the exact same thing. It just ends up being GME of 1/4 is, once I squared it, RE squared, right? And then you can see that this value, these are all the same variables of my 9.8. So really, I'm just saying what is 9.8 divided by 1/4, right? So you could flip and multiply, and really you're just going to get 4 times that. So our new gravity would end up just being 4 times that 9.8 meters per second squared, which is 39.2 meters per second squared. And that's really of 1/2 g. That doesn't look quite right, but it's half the distance. So I'm going to take that away because it's not really right. It would really just be our new g. So I'm going to put that. It's now new g. If you were halfway down, you would be accelerating at 4 times the speed because it's inverse, but it's also squared. So the smaller you get, the greater that attraction is going to be. It works in the same way, but opposite if we're going further from the Earth. So if I have my gravity is equal to GME over RE squared equals 9.8 meters per second squared. And then I want to figure out what gravity is if I say double the amount of distance. Then I'm going to say that's 2 times R of E squared, which is just going to give me GME over 4 RE squared. And as we can see, that is 9.8 again. And so it's just going to be it's going to be 9.8 meters per second squared divided by 4 this time instead of multiplied by 4. So our gravity would only be 2.45 meters per second squared if we just doubled the distance from the Earth, if we doubled the radius of the Earth. So you can see you're not accelerating very fast that far away. The reason that we don't look at this very much and we say that it's always 9.8 is because we're almost always on the surface. But very truthfully, gravity does change depending on your distance from the center of the Earth. It is an inverse square law, meaning it's going to change by the opposite of the amount you do with the distance, and it's going to be squared, so it's not a direct proportion. Okay, so inverse square pretty much tells you the exact relationship. You should be able to do something like this so that you can get new values with it.